So most people are aware the Earth is changing. But for the most part, what people have heard about when it comes to how the Earth is changing are things like climate change, invasive species, or biodiversity loss. But there are a couple other drivers of changes that are not really well known, and one of those is nutrient enrichment. So nutrient enrichment is when there is more nutrients in a system than is normal. So what does normal mean? So let's think about a world without humans. There's a certain amount of what we call reactive nitrogen, which is nitrogen that can be taken up by plants, which then can be taken up by herbivores and then predators, and kind of cycles through an ecosystem. That predator dies, it decomposes, and bacteria will take up that nitrogen. And eventually, some of that nitrogen is denitrified, which is a fancy word to just say that it goes from a reactive state to a gas, and the gas just goes up in the atmosphere. And that's basically the nitrogen cycle. But what humans have done is we have greatly increased the amount of nitrogen that is entering the biosphere. And how do we do that? Well, we do it for three major ways. First is the burning of fossil fuels. This is an indirect way. We're not trying to get reactive nitrogen into the world through fossil fuel burning. It's just a side effect of combustion. The second is the global use of nitrogen-fixing crops, such as legumes like soybeans. And then lastly, and by far most importantly, is the use of fertilizer. Humans have this love affair with fertilizer. Unfortunately, the fertilizer doesn't usually stay where you put it. And this is all causing problems, both in the terrestrial system, like the agricultural field where the fertilizer is actually added, and also in the aquatic system, where a lot of that fertilizer ends up anyway because it's leached and removed from the soil and added to these aquatic systems. So in both systems, there's a big disruption that's going on because the balance that has been here for millennia is completely thrown off.
The plants, they have two different strategies. They are either conservative or they are like acquisitive traits. So when we add nutrients, soil nutrients, it's like more of the species that are acquisitive in trait. They dominate because they try to take resources as much as possible, and they outcompete all other species. Whereas when we don't have nutrients addition, so it's like more species that are conservative.
And the plants that are really going to be able to take over are the plants that can basically utilize all that nitrogen and phosphorus as fast as it can for growth and then compete for light.
Like side ragweed. Now when they grow taller, they cast shadow all over the other species growing down, so that species growing underneath, they don't receive any light, and that means they cannot compete with the ragweed.
We're creating a global biosphere that is favoring invasive species. So overall, it's really important to get a better understanding of how nutrient enrichment is influencing the world. And so this brings us to the nutrient network. The nutrient network is an association of experiments across the globe with the main goal of trying to better understand the causes and consequences of eutrophication in grassland systems.
We have 8 different experimental treatments where we have used nitrogen, phosphorus, potassium, and micronutrients. So the main objective is to know what are the effect of land use change or fertilization on natural grasslands, species diversity, and productivity.
The importance of the nutrient network is the fact that we've got experiments that are covering the entire globe. And this is pretty rare. Most experiments, if you think about it, are done at one site, one location, maybe a couple locations in a single state. And you can still have a decent amount of power to ask some really good questions when you run experiments like that. But with the nutrient network, what we have is over 100 sites across the world that are all doing the exact same experiment. And that is really powerful. Because usually what happens is that when we try to better understand what's happening globally, we run statistical analyses that can look at a bunch of different experiments from a bunch of different papers and try to understand general patterns. But there's a lot of statistical power that's lost when you have to combine experiments that did completely different techniques. The power of the nutrient network is that every single site is doing exactly the same experiment. Now there's a little bit of variation when it comes to how many plots they have or how many blocks they have, but overall they are doing the exact same experiment. And of course the other really powerful aspect about the network is that it's global. So we have over 100 experiments over 6 different continents. Nutrient Network has been around since about 2007. That's when the first year of data was collected. At the beginning, there was about 50 sites that started. At this point, like I said, there's about 150 sites worldwide at this point. So the site that we work in is in Temple, Texas. And this is an association with the USDA ARS, which stands for the Agricultural Research Service.
So what we do is to collect the photosynthetically active radiation. We use the sensor to measure the light at the ground level and at the top of the canopy, so that we know how much light is passing to the ground. For species composition, we use 1 meter square quadrant within which we identify each individual species and identify what is the percentage that is covered by each species. So we fly drone over the dragnet and nutnet each month to see change in the composition, species composition over the time, and we fly drone for the 5 months of growing season starting from May to October. We collect soil samples from each of the plots to analyze any of the changes going in the soil, chemical and physical properties with our treatment. On other hand, Dragnet, which is recently established in 2019.
Dragnet is a offshoot in a way of Nutrient Network. Now it's still an independent experiment. You have about 25% of Nutrient Network sites that are also have a Dragnet site. So for the most part, 75% of Dragnet sites are completely new, which is fantastic. It means that more people are getting involved in research networks, which is really where we want science to be going in the future. So what is the difference between NutNet and Dragnet? Dragnet, we have incorporated disturbance as a treatment. And what that means is that for the first 3 years of the experiment, all the disturbance plots are actually plowed, and all of the rhizomes, which are the underground stems of plants where they can regrow from, have been removed by hand. This kind of disturbance is happening globally. So it's really important to understand how disturbance influences species composition, biodiversity, the plant community's ability to resist and recover from disturbance. So what Dragnet does is it actually combines these two factors into one experiment. So you have disturbance crossed with nitrogen enrichment. So what does cross means? It means that some plots only have disturbance, some plots only have nitrogen and phosphorus enrichment, and then some plots actually have both. And then obviously we put a control in there where we don't do anything, so we can compare what's going on in the treatment plots to what's happening in the control plots, which gives us a baseline of change.
Mainly the objective of doing so is to understand how grassland responds or how grassland recovers back from the human disturbances or the kind of anthropogenic disturbances that we have common in the grasslands. In the first year of our experiment, what we saw is like we had some of the species that did not occur dominantly, but in the second year of the experiment, when we rolled our experiment of fertilization and soil disturbance, we saw distinct species compositional change. So for example, in the plot where we disturbed the plots, we saw a lot of ragweeds dominating. So those were more dominant in the disturbed plots, but when we have plots where we have fertilized, we saw a lot of Johnson grass. But when we combined the soil disturbance and the fertilization, we saw again ragweed dominating those plots. So these were the first year. So in the first year we saw that ragweed, they were not very super tall. They were like 5 feet, 6 feet tall. But in the second year of the data collection, we realized that the ragweed that we found in the disturbance fertilized plots, they had grown way taller than they used to be, like maybe 9 or 10 feet. So basically the concept of having higher species diversity is like they have differential response to different disturbances. That provides the insurance that whenever we have disturbance like maybe drought or say maybe insect outbreak, then if it's monoculture, we're gonna lose all the grassland species. But if we have different species or we have number of species with the different responses to those perturbation or the disturbance, then we might have chance that they're gonna respond differently and then be able to maintain the ecosystem services.
So why do we study grasslands? Well, grasslands are an incredibly important ecosystem worldwide. And unfortunately, they're also in some ways an endangered ecosystem. In North America, only about 1% of the native prairies exist. And you might wonder what happened to the rest of the 99%. Well, unfortunately, we have converted all of that land into agricultural lands. It just so happens that grassland makes the perfect agricultural field, right? You've got beautiful soil, there's a bunch of organic matter in the soil, and you don't have to remove trees or anything, so it's just the perfect place to set up shop if you want to grow crops. So we care greatly about what's happening in grasslands, both in more natural systems and both in agricultural systems. Grasslands also hold a really large amount of carbon in their soil, and as such, we really are interested in how much carbon is going to be held in there as eutrophication increases, as climate change increases, as invasive species become more dominant. Are these systems going to hold more carbon? Are they going to actually hold less carbon and actually contribute to climate change? These are really important questions that we are trying to answer through experiments like Nutrient Network and Dragon.